Welcome to Raw History. Here, we cut through romanticization and speculation to show you, well, the unfiltered reality of human history. Picture this. It's 950 CE in Norway, and the temperature has plummeted to -20 degrees Celsius. Snow piles waist-high outside, and the wind screams across the landscape like a living thing. Inside a Viking longhouse, families gather in relative comfort, children play, and craftsmen work on their tools. No central heating, no insulation foam, no double-glazed windows, just ancient engineering that, honestly, modern science is only now beginning to fully appreciate. Archaeological excavations across Scandinavia, from Borg in Lofoten to the reconstructed sites in Iceland, have revealed construction techniques so sophisticated that they challenge our assumptions about so-called primitive building methods. The forgotten science of earth and wood. Viking builders understood something that took modern architects centuries to rediscover: thermal mass. Excavations at sites like Trelleborg and Fyrkat in Denmark have revealed wall compositions that honestly go far beyond simple mud and sticks. The wattle and daub technique employed by Viking builders involved a really precise mixture of local clay, straw, animal dung, and, in some cases, even animal blood as a binding agent. This wasn't random. Each component served a specific thermal purpose. The clay provided density and heat absorption. The straw created these microscopic air pockets that trapped warmth. Animal dung, which is rich in fibrous material and natural oils, added water resistance and flexibility to prevent cracking during freeze-thaw cycles. Archaeological analysis of preserved wall sections from the 10th century shows layers sometimes reaching as much as 30 to 40 centimeters thick, creating substantial thermal barriers. The timber framework itself represented another layer of thermal engineering. Rather than just nailing boards together, Viking craftsmen used interlocking joints cut with precision axes and adzes. These joints minimized gaps where cold air could infiltrate. Dendrochronology studies of timber from excavated longhouses in Hedeby and Ribe confirmed that builders selected specific tree species, primarily oak for its density and rot resistance, and allowed the wood to season properly before construction. This attention to material selection wasn't just about aesthetics, it was in fact survival engineering. Dense, properly seasoned timber conducts less heat than fresh wood, which creates a much more effective thermal boundary. The multi-layered defense against cold... Well, that's where the genius of Viking thermal engineering really becomes clear. When you examine their layered approach to insulation, archaeological evidence from sites across Iceland, including the well-preserved remains at Stung and Þjórsárvöllur, reveals walls constructed in distinct layers, each one serving a specific function. The outer layer typically consisted of stacked turf blocks, cut to pretty precise dimensions and laid almost like modern bricks. These weren't just casual chunks of grass-covered dirt. Excavations show turf blocks measuring approximately 30 by 40 by 10 centimeters, carefully selected for their dense root systems that held the blocks together while also providing crucial insulation. Beneath the turf layer, builders installed the wattle and daub structure, creating an air gap of several centimeters between the outer turf and inner wall. This gap wasn't accidental. Modern thermal imaging of reconstructed Viking longhouses has demonstrated that this dead airspace acts as a convection barrier, preventing cold from conducting directly through the wall. The Vikings discovered through trial and observation what we now call the cavity wall principle, a technique not widely adopted in European architecture until the 19th century. The interior wall surface presents another innovation. Archaeological finds from Borg, the largest Viking longhouse ever discovered in Norway, show evidence of wooden paneling installed on the interior walls. These panels, typically made from split logs smoothed with draw knives, created yet another air gap and provided a warmer surface for inhabitants to lean against. Some excavations have revealed remnants of animal hides hung on these panels, adding another insulation layer and decorative element. The walls weren't just barriers, they were thermal systems designed through centuries of accumulated knowledge. Heat generation and retention strategy. The central hearth, or arin, served as more than a cooking fire. Excavations consistently show these hearths positioned precisely in the center of the main hall, equidistant from all walls to ensure even heat distribution. The hearth design itself reflects thermal understanding rather than simple fire pits. Archaeological evidence reveals carefully constructed hearths with stone foundations that absorbed heat during the day and radiated it throughout the night. Some sites, show evidence of clay-lined hearths with channels that directed hot air under sleeping platforms, an early form of radiant floor heating. Smoke management represented another thermal consideration. While popular imagination pictures smoke-filled longhouses with simple roof holes, excavations actually paint a more sophisticated picture. The smoke hole, or jori, was carefully sized and positioned to create a draft that pulled smoke up and out, all while minimizing heat loss. The rising smoke actually heated the turf roof from below before escaping, turning what would otherwise be a waste product into a heating element. Analysis of soot deposits on preserved roof timbers from sites like Lens aux Meadows in Newfoundland, well, it confirms this smoke heating effect. The integration of living space with livestock areas wasn't just about convenience or space efficiency. It was, in fact, thermal engineering. Body heat from cows, sheep, and goats housed in the byre section contributed measurably to the internal temperature. Studies of reconstructed Viking longhouses with livestock present show temperature increases of 4 to 6 degrees Celsius compared to structures without animals. The Vikings understood that every heat source mattered when facing 6-month winters. The Viking approach to thermal construction offers lessons for contemporary sustainable architecture. Their reliance on locally sourced materials, earth, turf, timber from nearby forests, minimized transportation energy while providing excellent thermal performance. Their layered insulation strategy achieves results comparable to modern construction without petroleum-based products. So current sustainable building movements are, really rediscovering these principles. They're incorporating things like thermal mass, cavity walls, and natural materials into designs that are often marketed as, innovative breakthroughs. But the real innovation, honestly, wasn't about having modern materials or a scientific understanding. It was all about observation, adaptation, and the accumulated knowledge that was passed down through generations. Viking builders, for instance, couldn't calculate R values or model heat transfer equations, but through experience and necessity, they managed to develop solutions that actually worked. Every longhouse was, in a sense, an experiment, every cold winter a test, and every surviving family was proof of successful engineering. These ancient builders faced impossible odds and, they won through ingenuity, observation, and a deep understanding of their materials and environment. Their walls weren't just shelter. They were, in fact, climate control systems that kept families warm through the darkest, coldest months when failure really meant death. If this deep exploration into Viking engineering has sparked your curiosity, then, subscribe to Raw History for more evidence-based investigations into humanity's forgotten innovations. Share this with fellow history enthusiasts who appreciate the unfiltered truth about our ancestors' remarkable achievements. What other ancient technologies should we investigate next? Let us know in the comments below.